Welcome to The Explainer. When you're standing on a platform waiting for your commute, it's so easy to just focus on the massive steel trains, the endless tracks, and all that heavy engineering. But today, we're taking a masterclass in the invisible infrastructure that's actually keeping millions of passengers safe every single day. We're going to completely reframe how you look at trains by exploring railway telecommunications as the biological nervous system of the railway. It's hidden, it's incredibly fast, and honestly, in an emergency, it's the only thing standing between safety and total disaster. So here's our roadmap for today's explainer. 1. The railway's nervous system. 2. Halting trains with GSM-R. 3. Managing safe passenger evacuation. 4. Supporting first responder communications. And 5. Operational connectivity and SCADA. Let's get right into it.
Section 1. The railway's nervous system.
The absolute most crucial point to understand right out of the gate is the difference between mere movement and actual operations, right? Like, a train can technically roll along a piece of track without telecommunications, but it absolutely cannot operate safely, efficiently, or respond to danger without them. And this brilliantly illustrates the central metaphor we're running with today. Think of telecom networks as the body's emergency systems. They provide the instantaneous reflexes required to stop a speeding train. They act as the voice used to guide panicked crowds to safety. And they're the vital organs that manage and control immense, lethal electrical power during a crisis.
Moving to Section 2, halting trains with GSM-R.
So imagine a hazard is suddenly spotted on the line ahead. Maybe it's a derailment or a vehicle stuck on a level crossing. How do you instantly stop hundreds of tons of metal moving at high speed before it's too late? Well, the answer is GSM-R, which stands for the Global System for Mobile Communications Railway. Now, this isn't just a regular cell phone network. It's a highly secure, digital network built specifically for the railway. To make sure a public cell phone dropped on the track or, say, a wildly busy New Year's Eve network doesn't interfere with train safety, GSM-R operates on highly regulated, dedicated spectrum bands. Specifically, we're talking about the uplink bands of 876 to 880 megahertz and downlink bands of 921 to 925 megahertz. This dedicated space means emergency signals literally never get a busy signal.
If you look at the physical GSM-R terminal interface used by a signaler or a driver, you'll see this massive big red button. That's the emergency call key. Hitting that button initiates a Railway Emergency Call, or REC. It's a high-priority function designed specifically for a level of danger that requires all railway movements in a predefined area to just stop completely, immediately.
Let's walk through the exact rapid-fire sequence of an REC. Step 1. A hazard is identified by a driver or a signaler. Step 2, they smash that red emergency call key. Step 3 is where the magic really happens. A 5-second burst of a highly distinctive emergency tone is instantly broadcast into the cabs of all trains within that predefined geographical network cell. And Step 4, every single driver hearing that tone knows they must brake and halt their train immediately. It's an automatic, area-wide reflex action that saves absolutely vital seconds.
Section 3. Managing safe passenger evacuation.
Okay, so we've stopped the trains, but what about the dense crowds inside the actual stations? Imagine a fire suddenly breaks out in a deeply crowded subterranean concourse. Think about that scenario for a second. How does a station react instantly to a fire before a human being even has time to pick up a microphone or flip a switch? Because in a fire, manual intervention is just way too slow. The station itself literally has to become a machine designed to expel passengers to safety. And amazingly, it does exactly that through automated fire panels. The very moment a fire actuator is triggered, a massive, simultaneous automated chain reaction begins. The system instantly closes fire dampers in the ventilation system to choke off the oxygen supplying the fire. It automatically throws open all the ticket gates so the exit is completely frictionless. It takes over the lifts, immediately moving them to a floor deemed safe and locking them out of service. And crucially, it automatically triggers announcements to manage crowd panic.
Those automated announcements run through what's known as a PAVA system, which is a public address voice alarm. Now, the key takeaway here is that PAVA isn't just your standard set of ceiling speakers. When a fire breaks out, standard wires melt and the power goes out. But PAVA systems, they're built with specialized fire-safe wiring and their own auxiliary battery power sources. They are specifically engineered to survive extreme heat and main power loss, so they can keep broadcasting clear, highly intelligible evacuation instructions even during maximum chaos.
Moving right along, Section 4, Supporting First Responder Communications.
So the passengers are evacuating, and now the emergency services are arriving on the scene. When paramedics and firefighters show up, they obviously bring their own radios. But what happens when the emergency is 30 meters underground? Well, a subterranean tunnel environment is a total communications nightmare. Standard radio waves simply do not penetrate solid rock, earth, and thick concrete. If firefighters go down there with their standard radios, their signal just drops dead. So the railway has a strict mandatory obligation to provide specialized infrastructure to extend the emergency services reach right into these dark zones. You see, the physics of radio frequencies behave very differently underground. The physical dimensions of the tunnel and the frequency band you use dictate everything. For instance, if emergency services are using a 450 megahertz frequency from a tunnel-mounted aerial in a tight single-bore tunnel, that signal might only travel about 500 meters. But if you bump that up to a higher band, like 900 megahertz, in a wider double-track tunnel, that signal can suddenly travel 2 kilometers or more. But even with that extra range, the curves and long distances require a dedicated physical engineering solution. And that brilliant solution is known as the leaky feeder. It is exactly what it sounds like, actually. It's a radiating cable strung continuously along the ceiling of the tunnel that intentionally leaks radio signals out and receives them back in. It essentially functions as one giant, continuous antenna running the entire length of the tunnel. This guarantees that a paramedic deep underground never loses voice contact with the incident commander up on the surface.
And that brings us to Section 5, Operational Connectivity and SCADA. All right, we've secured the trains, the passengers, and the first responders. But there is a massive, invisible elephant in the room here: electricity. SCADA stands for Supervisory Control and Data Acquisition. If the telecoms are the nervous system, SCADA is controlling the heart of the railway, which is the immense electrical power driving the traction systems. During an emergency, say a derailment or a structural collapse, you have to be able to safely distribute or completely isolate and shut off massive amounts of high-voltage electricity instantly. If you don't, rescue workers risk being electrocuted.
Managing all this safely requires an ironclad pairing of data and voice. First, you absolutely need high-availability SCADA data links. These are the digital commands that physically throw the massive switches to cut the power to a crash site. But equally as important, you need rigorous voice protocols. Before anyone even thinks about stepping onto that track, controllers and ground staff use highly secure voice lines to confirm, double-check, and humanly verify that the power is indeed completely dead.
Because SCADA is so incredibly critical for emergency power isolation, we literally cannot allow a single point of failure. The survivability of this system is just heavily engineered. It uses dual or multi-routed data links, meaning if one fiber optic cable gets severed in a crash, the data instantly takes a totally different physical route. There are alternate control sites ready to take over at a moment's notice, robust, precise false alarms tell operators exactly where a break happened, and the whole shebang is backed up by uninterruptible power supplies, or UPS. So even if the entire grid fails, the control system stays fully alive.
Okay, let's bring this all together. When you buy a ticket and sit down on a train, you're experiencing the end result of millions of hours of engineering. You see the comfortable seats, you feel the smooth ride, but it's this hidden web of telecommunication engineering, the GSM-R emergency calls, the automated PAVA fire systems, the leaky feeders, and those critical SCADA power networks that acts as the invisible nervous system, truly guaranteeing your safety.
So I want to leave you with a thought for the next time you're on your daily commute. When your train glides into a deep, dark concrete tunnel, look out the window into that blackness and just ask yourself, what invisible signals are pulsing through the rock right now, constantly communicating, monitoring, and keeping me safe? Thanks so much for joining me on this deep dive on The Explainer.